Welcome to MEI Mechanics. We're on the topic Impulse and Momentum 2, Collisions in 1D, and this is video 2.2, Loss of Energy due to Impact. Now, our modelling assumption always, when we're dealing with collisions in this course, is going to be that there are no external forces acting during that collision. So the only thing that we need to consider is the momentum of each of the objects before and after the collision, which depends on the masses and the velocities of those objects. Because momentum is basically always conserved, the total momentum, there'll be no loss of total momentum. The total momentum will be the same before and after the collision. But that's not true of kinetic energy. Most of the time kinetic energy is lost during collision, and we can sense that loss in real life. If two objects collide, we usually hear a sound. Where's the energy come from to make that sound? That's come from the kinetic energy of the objects. Also, the objects will be slightly warmer after the collision because some of the energy has been transferred into heat. Again, that's come from the kinetic energy, which means that kinetic energy is always lost in collisions. Now, if we think about this idea of the coefficient of restitution that we've met already, that's a measure of how elastic the collision is, and that's going to determine what proportion of the kinetic energy is lost. Now, remember that number has to be between 0 and 1, so if we imagine a sort of perfect situation where we had a perfectly elastic collision, then there would be no loss of energy. If E is anything less than 1, then there will be some loss of energy, and so the change in the kinetic energy will be the final kinetic energy take away the initial kinetic energy, and that will be a negative number, indicating a loss in energy. So here's a simple example. We have two objects here. This object of mass 6 kilograms with an initial velocity of 4 meters per second. This one, which is 1 kilogram, which is at rest, and then after the collision, this has a velocity of 3 meters per second. This has a velocity of 6 meters per second, and the coefficient of restitution there is 3/4. And that's consistent with these because they're approaching each other with a relative speed of 4 meters per second, and afterwards they're because they've got a difference in speed of 3, that means they're moving apart from each other at 3 meters per second. So the speed of separation is 3/4 of the speed of approach. What we want to work out is what the change is in the kinetic energy here. So all we need to do is calculate the kinetic energy beforehand. So before the collision, we've got a half times 6 times 4 squared, so half times that mass times that speed squared, and then this other object, because it's at rest, has a kinetic energy of 0. So that is a kinetic energy before the collision of 48 joules. After the collision we have a kinetic energy of half times 6 times 3 squared, that first object there, and now this other object has non-zero speed. That's half times its mass, which is 1, times its speed, which is 6. So that is a kinetic energy of 45 joules. So before we had a kinetic energy of 48, we've now got a kinetic energy of 45 joules. So the change in kinetic energy, final kinetic energy minus the initial kinetic energy, so that is a change of minus 3 joules, which is negative as we expected because that indicates a loss in kinetic energy. Here's another example, a little bit more complicated than the last one in that they both have an initial speed, and this one we have to be careful with the direction. Even though the arrow is to the right, the number is negative, which indicates this thing's actually moving to the left after the collision. So the kinetic energy beforehand is half times mass of 3 times speed of 6 squared, and then for this object, half times 4 times 2 squared, which is 62 joules. And then after the collision, well, we have a half times 3 times, well, never mind what direction this is going in, it has a size, the size of that velocity is 2, so the speed is 2. That's the thing which, when we square it, it will be 4, so we can afford just to say 2 squared there, plus a half times this massive 4 times 4 squared, which is 38 joules. So again we can see there's a change in kinetic energy, final kinetic energy minus the initial kinetic energy, that's 24, minus 24 joules. Now in this example we are told that the particles coalesce during the collision with a final combined speed of 0.8 meters per second. If they coalesce, that means that their speed of separation is 0, and that means that the coefficient of restitution must be 0. And so the kinetic energy beforehand is a half times mass times speed squared for the first object, plus a half times the mass times the speed squared. The second object, again, they're in different directions, but that doesn't matter when the speeds which are being squared. And then and that works out as 40 joules. Now afterwards, we can work out, we've effectively just got one object, so its kinetic energy is a half times its mass. Now this has come from joining these two objects together, so 3 kilogram and 2 kilograms. So this combined object has got a mass of 5 kilograms, and we're told that it has a speed of 0.8 meters per second, and that's 1.6 joules. So the change in kinetic energy is 1.6 minus 40, so that's minus 38.4 joules. So that concludes video 2.2, loss of energy due to impact. The next video will be 2.3, successive impacts of spheres.